Hey everybody. I'd like to take a minute to walk you through the key for the enzyme quiz, as well as to explain some misunderstandings and misconceptions, as well as some common pitfalls that I've seen from the quiz. Now, all right, we'll get started. Okay, so the first question is a problem where I'm asking you to predict the mechanism of an enzyme based on the substrate and the amino acids that are contained in the active site. Now, there are two enzyme mechanisms in your toolkit that you have to work with. You have a serine protease, which is chymotrypsin, and you have an aspartate protease, which is HIV protease. And based off the composition of the active site of papain, you should be able to predict which mechanism this will be more similar to. So clue number one, it's a cysteine protease. And so the structure of cysteine looks a lot like serine, except it has an S instead of an OH. Also, you'll remember the pKa of cysteine is a lot lower than it is for serine, so a pKa of 8.4. And if you look at the periodic table, sulfur falls under oxygen. So and also in our table of nucleophiles from the enzyme mechanisms lecture, you would have seen that that negatively charged sulfur ions or thiols, deprotonated thiols, act as good nucleophiles. That and the fact that there's a catalytic triad, so it contains a histidine, which you know is in the chymotrypsin mechanism, as well as asparagine, and there's an aspartate in the chymotrypsin mechanism, should have been a giveaway that this enzyme was going to act like chymotrypsin. And most, if not all of you, were able to make that logical jump to the fact that this must be an enzyme that acts like chymotrypsin. A common mistake was to get confused about, I think perhaps some of you read asparagine and processed aspartate. So if you used aspartate instead of asparagine, you lost a point on the active site portion. If you neglected drawing asparagine in the active site altogether and just had the histidine and the cysteine, you lost 2 points. And so what asparagine is going to do is it's going to act exactly like aspartate, except it's going to hydrogen bond with the general acid base catalysis of histidine, except it's going to act either through its double bonded O or through the lone pair electrons of nitrogen on the side chain. I would think it would happen through double bonded oxygen, but it could also make sense that the nitrogen could hydrogen bond, so I gave credit for either. Now, once you draw out the active site of papain, where you have the cysteine, the histidine, and the asparagine all lined up, the correct approach would have had cysteine to act as the place of the serine, and the mechanism would proceed exactly like with the serine protease, except cysteine would be doing the nucleophilic attacking instead of serine. Some of you went and had asparagine or histidine act as a nucleophile, and histidine won't act as a nucleophile in this case. You can't see it very well drawn out, but those R groups contain bulky side chains. So you wouldn't be able to have a relatively large ring like histidine attacking that electrophilic carbon. You would really need cysteine there. And asparagine also would probably be too bulky to be doing a nucleophilic attack. And asparagine is generally not one that we see doing attacking in mechanisms, especially because that nitrogen does not have a pKa and it doesn't lose and accept a proton. So again, cysteine here is really the only reasonable option to be having do that mechanism. And so again, the mechanism processes exactly like we would see with chymotrypsin. We go through the cysteine makes a nucleophilic attack. We see the histidine acts as a general acid base, just like it does with chymotrypsin. We form a tetrahedral carbon intermediate. And that's an arrow, not a double bond. Then first the amine portion of the peptide leaves, and then we're left with an acyl enzyme intermediate. Histidine will again switch around to do another round of general acid base catalysis by deprotonating water. Water will make a nucleophilic attack on the electrophilic carbon, and then when the electron density collapses, the cysteine residue is free to leave. Now, somebody had asked in problem session why you wouldn't just have another amino acid within the active site make the attack. Why do we need water? It's because we need something to add to the carbon that will cause the protein, the substrate protein, to be released from the enzyme. We don't want the peptide stuck in the active site because that enzyme can't go seek out, papain can't go and seek out other proteins to chew. So we have to add something to act as a nucleophile that's not attached to the protein. And in this case, that's water. Because if you remember, the concentration of water in water is 56 molar. There's a lot of water that can then be pulled into the active site and used strategically. So the other question was, how does this mechanism work? Well, Adolph's, okay, so papain chews down amide bonds, and it's very non-specific. So it's not like chymotrypsin, which is going to go after big flat aromatic amino acids only, or trypsin, which is going to go after long, skinny, positively charged amino acids. In enzymology, it's what we call a promiscuous enzyme. And so this is going to be really good at tenderizing meat because it's just going to chop down a lot of peptide bonds in the meat, which will make it softer. But also, the venom in jellyfish and bees has proteins in it. So it could also work to break down those venomous proteins that cause the sting and the itch. All right, so moving on to enzyme kinetics and perhaps slowing down a little bit, you were given kinetic data for what we would call a putative dihydrofolate reductase enzyme from tardigrades in the presence with a substrate dihydrofolate, and also in the presence of an inhibitor, methotrexate. And so you were given this table and you had to fit the data to figure out, first of all, whether or not the enzyme works, second of all, whether the inhibitor works and what type of an inhibitor it is, and then determine the Km and the Vmax. Now, if you had a Sigma plot or some other fancy plotting software, you could plug these data, apply a hyperbolic fit, and then do the hyperbolic fit, and then apply the Michaelis-Menten equation. To figure out what the Vmax and Km and then the Vmax apparent and the Km apparent are. However, most of you really just only have Excel to work at, so the technique that you're going to go to is the Lamy-Verburg method, even though we showed in class that in certain circumstances it can be flawed. But either way, for the purposes of you guys, it's a good starting point. Okay, so if we have our Lamy-Verburg plot, we have 1 over the velocity on the y-axis, and so the units are inverse of the units, so that would be minutes per nanomole, and on the y-axis we'll have the concentration of DHF in micromolar, or if we invert it for the Lamy-Verburg plot, because it's a double reciprocal plot, 1 over micromolar. And so, again, we can fit these data to a line because when you do a double reciprocal plot, you magically linearize things. And so if we look at the equation y equals mx plus b, we can split that up into the slope being equal to the Km over the Vmax, and then the b being equal to 1 over Vmax. So the way you will want to approach this, if you're solving for your data, is you're going to want to solve for the easy thing first. And if we look at b only has one component equal to it, and that's 1 over Vmax. So what we would do is to find the Vmax, we would take 1 over b. And then, if we know the slope of the line is equal to Km over Vmax, we can then multiply Km over Vmax, or the m, by Vmax, which we got from b, to give us the Km. Now, I got a lot of funky units for this, or I got no units at all. And so if you just didn't put any units, you just looked at it and were like, I can't handle these units, you lost 2 points. The reason being, if you don't give me units, I don't know what your answer is. So your unit could be units of guinea pigs, of kilograms per second, whatever. So you always need to make sure to include your units. But in this tutorial, I'm going to assure you and show you that the units work out. Trust me? Okay. So in particular, you want to pay close attention to the units of velocity. a lot of you guys put nanomolar or nm instead of nanomoles, and if you did that, you lost a point, because in this case, the units are nanomoles of enzyme produced, not nanomolar. And again, the units on the y don't have to match the units on the x. It's okay, it works out. And so if we look at the units of the slope, so the way we calculate the slope is we do the rise divided by the run. And so if the units on our rise are minutes per nanomole, and the units on our run are 1 over micromolar, if we have minutes over nanomole divided by 1 over micromole, that gives us units of micromolar per minute over nanomole. And again, if that freaks you out, it's okay. You don't have to worry. It's all going to cancel out, and you're going to get the right units for your Vmax and the right unit for Km. Just trust me. Okay, so let's start with calculating the Vmax for the enzyme and the Vmax for the apparent for the enzyme plus inhibitor. So to calculate the Vmax for the enzyme alone, by the way, if you're looking at the inhibitor, the enzyme is always going to be the lower of the two slopes. So if we look at the enzyme, we can calculate the Vmax from 1 over B, which in this case is 1 over 0.1045. And the units, again, for that are going to be minutes per nanomole, because that's the units on the y-axis. So if we solve for Vmax is equal to 1 over B, so it's equal to 1 over 0.1045 minutes per nanomole, we get a velocity of 9.56 nanomole per minute. And again, those units are going to be inverted from what you see on the y-axis. Don't panic. It makes sense because your velocity is your Vmax, whereas your y-axis is 1 over a velocity. You would apply the same treatment to the enzyme plus inhibitor, and that you would do 1 over B, so 1 over 0.0917 minutes per nanomole, to get a Vmax apparent of 10.9 nanomoles per minute. Okay, so next we have to figure out the Km. So our Km is equal to the slope times the Vmax. And so for the enzyme alone, our slope is 0.19, and our units for our slope we worked out were micromolar times minutes over nanomoles. So if we have our slope of 0.19 micromolar per minute over nanomole, micromolar times minute over nanomole, if we multiply by the Vmax, which has units of nanomole per minute, the minute and the nanomole both cancel out, and we get a Km of 1.82 micromolar for the enzyme alone. And that makes sense. So again, the units for M are really scary, but now you can trust me and have visual proof of the fact that the units work out, even if you don't have micromolar for substrate and micromolar per minute or whatever on the Y. We can take the same approach when solving for the Km for the enzyme plus inhibitor, and we can take the slope 0.9992 micromolar times minutes over nanomole. We multiply it by the apparent Vmax of 10.9 nanomoles per minute, and we get an apparent Km of 10.8 micromolar. Okay, so now you need to take the Vmax and the Km and the presence and absence of inhibitor and make a decision about what type of inhibitor this is. And so first things first, you see that the Km is going to increase, and it increases literally by an order of magnitude in the presence of inhibitor. The Vmax looks like it goes up a little bit, but in truth, this variation is probably within the error of the measurement. It's one thing to double, to be 5 times bigger, or even be an order of magnitude bigger, and then another to be like less than a 5% difference. So we can just make the assumption here that the difference in the Vmax is negligible, whereas the Km apparent is much bigger than the Km for the enzyme alone. So in this case, because we see the Km increases, but the Vmax doesn't really change, this would be consistent with the mechanism of a competitive inhibitor. So methotrexate is a competitive inhibitor. And if you were to now go on the internet and look up methotrexate, you would confirm that yes, methotrexate is a competitive inhibitor of dihydrofolate. The next question is whether or not you think this enzyme actually is dihydrofolate reductase. Because remember, the prompt for the problem is you're trying to figure out whether this gene in a tardigrade contained codes for the protein, the dihydrofolate reductase for tardigrades. And so we have two indicators that this would be dihydrofolate reductase. The first would be the fact that there's a slope in the presence of DHF. So the fact that we see a Km and a Vmax in the presence of DHF means that the enzyme works on DHF. The second clue is the fact that the enzyme is inhibited by methotrexate. That would suggest to us that this enzyme is methotrexate. Now, other steps would have to be taken where we would look at other potential substrates and we might want to crystallize the protein to confirm that it's dihydrofolate reductase even further, because there are other enzymes that work on folates, but this is an indication that we would be on the right path. And then the last question that I want to address is whether or not this is a good fit, or whether or not the Lineweaver-Burke method is a valid approach for this method. And that's because I think there was a little bit of confusion from class when we did the Michaelis-Menten fit. So one thing that doesn't change is that the direct fitting method, so making a hyperbolic plot of your data and then directly fitting the Michaelis-Menten approach, is always the best approach. And if you're going to be publishing kinetic data in the literature, you should be directly fitting your data. And in class, we saw an example of where Lineweaver-Burke absolutely fails, right? But if you have data that are really good and are well acquired, and your lowest point is high enough above the noise, you can actually have a Lineweaver-Burke fit give you answers that are consistent with the answers you would get from a hyperbolic fit. So, how do you know whether or not a Lineweaver-Burke is a good enough fit? Okay, so if we were to look at our data table here, if we look at the initial velocity with DHF, we can see it levels out around 10 nanomole per minute. So we're going to want to see a Vmax of around 10 nanomole per minute. And the Km, so if we go to 10, we divide it by half, we're going to want to, so we have an initial velocity of 5.8 at 2.5 micromole, we're going to see a Km of around 2 micromolar. And if we look at our answers from our Lineweaver-Burke plot, we get a Vmax of 9.6 nanomole per minute, check, and we get a Km of 1.82, check. So our Lineweaver-Burke is giving us an answer that lines up with what our data, before we double reciprocal the crap out of them, would expect us to get. So that's clue one. The second clue is if you actually look at the line is going through all of the points. And if you were to go in Excel and you were to take out that last point, you'd probably still get a very similar answer with or without that last point. Because that last point is the one that tends to make the Lineweaver-Burke problematic because it's the smallest concentration. Now, I think a lot of you were confused because a lot of you referred to this point as an outlier. But the fact is that this point is just because this point is far away from the other points on the axis does not mean it's an outlier. It just looks further out because it has a bigger magnitude when you divide it because it's a smaller fraction. So 1 divided by 0.1 is a lot bigger than 1 divided by 0.5. This is 10 versus 2. Okay. So what would make this, where the problem comes in with this point is that so this point is fine, but if we were under different circumstances where the signal to noise ratio of this particular concentration was big, we would run the risk of this point oscillating if there was a large error associated with that measurement, which isn't the case for this particular data set. If we had some wiggle in that point, we could see how these data could get skewed if the point was up there or if the point was down here. So that's what would make it an outlier. If all of these points down here appear to be on a straight line, and then this point is way off here or way down there, that's when you have a problem. And that's your clue that, hey, maybe these data are noisy and maybe I should rethink either this fit or maybe I should rethink using that point and starting at a higher concentration. But if all of the points match up together nicely on a line and you have a really nice high R squared, then the Lineweaver-Burk are probably accurate. So look at the line. Are all the points there? And then look to see if the answers that you get from your Lineweaver-Burk plot match up with what you would predict from the table. All right, that about covers it. As always, email me if you have any questions.